Alright, so let's recall that in the last video we were discussing finite arithmetic progressions in which all the terms are prime, and not just that, consecutive primes. And we have already seen two examples of this. And then the author says that most recently a sequence of 10 consecutive primes has been found. Well, it's an old book. Now it's an old book, so most recently means for us long ago. And in that sequence, the smallest prime has 93 digits, so it's a large number. And the difference between consecutive terms is 210, which we also know as the common difference in an AP. And then the author remarks that it will take some time before someone finds such a sequence with 11 terms. For 10 terms, it has already been found. So, for 11 terms, who knows? Now, I am not entirely sure if it has already been found. Okay, so you can try to see on the net. However, if one lifts the restriction that the primes have to be consecutive, then such a sequence with 11 terms can be found in which all the terms are still prime but not consecutive necessarily. And one such sequence is this, where the general term is this. Plus times n, where this is the range of n. N takes all the integer values between 0 and 10 inclusive, so you will get 11 terms. It turns out that all of these 11 terms, of course it will be in AP, and all these 11 terms turn out to be prime numbers, but they are not consecutive. Now, besides these considerations, mathematicians have also been interested in finding functions which will give us all primes. Okay, functions means functions whose input are integers and the outputs are all the prime numbers. However, if this cannot be managed, then at least we should have such a function in which the outputs are always prime. The outputs may not be all the primes, but they are always prime. And people tried to find such functions, and for a long time it was believed that this polynomial always gives us prime number for every non-negative integer n. But that is false. Of course, it's false. Leonhard Euler in 1772 showed that this is false. And well, I think it's a little stupid, don't you think? If you take n equal to, for example, 41, that itself will give you a composite number. I don't see what took them so long to see this, but maybe something. Okay, they could not think of the fact that this can be composite. And in fact, it is actually prime for all these values of n, starting from 0 and ending at 39. Okay, so all these 40 values of n, that too they are consecutive. If you put all of them, you get these numbers, and it turns out that they are all prime. So that led people to believe that this is always going to be prime, that it's a prime producing function. Not in the sense that it gives us infinitely many primes, that there are infinitely many n for which this is prime. Not like that. People believe that this is going to give us only primes, but that is false. For example, if one calculates, say, f of 40, then one would get this. Now, if you take 40 common out from the first two terms, then you get this, right? That means 40 times 41 plus 41, which means then again if you take 41 common out, you again get 40 plus 1. So you end up getting 41 square. That's composite. Similarly, the other one, there is another example which I was talking about just now. It is the one you get by taking n equal to 41. This is so silly. I mean, how can someone not see this? You straight away take 41 common out. You are left with what? 1 from here and 1 from here will get you 2. So 41 times 43. However, one thing is still impressive though, the fact that for all these consecutive values of n, the function values are all prime. That is still impressive. Okay, and people started searching for other such polynomials. It turns out that the next value for this polynomial, it actually came to be known as Euler's polynomial because of this, I think. The fact that he showed that this is not always prime producing. So the next value again turns out to be prime, and that is 1847. And the fact that this polynomial gives us so many primes continues to be true. For the first 100 integer values of n, Euler's polynomial gives us 86 primes, which is a very good record. But there are other polynomials also like this. For some time, people tried to come up with new polynomials which would give us more and more primes as their values when they are evaluated at integers. Another such polynomial is this. N square plus n plus this integer. Note that in Euler's polynomial we had, the polynomial is n square plus n plus 41, and 41 itself is a prime. Here also this is a prime, okay. And this is, it also still gives us many primes. G of n is prime for this many values of n. For so many values of n, it is prime, and all those values lie in this range. Whereas its famous rival yields this many primes, less number of primes. Now, I'm a bit confused here. What does the author mean by the famous rival of G of n? Does he mean Euler's polynomial f of n? I'm not entirely sure, okay, maybe. It is now known that no polynomial of this form, where q is a prime, can do better than the Euler polynomial in giving primes for successive values of n. Okay. Other polynomials may give more primes, but for successive values of n, Euler's polynomial is the best in this class of polynomials which look like this, n square plus n plus a prime number. And there are other polynomials also which give us primes. For example, we have this. These other polynomials, of course, are not of this form. Okay, they are of some other form, but still quadratic polynomial. Another one of such is this minus 3945n plus 34381. It was discovered in 1988, long ago, 4 years after I was born. And this polynomial gives us 43 primes for these values of n. These are also consecutive. The first 43 non-negative integers, if one puts in this polynomial, you will continue to get prime numbers. And there is another one also which gives us 45 primes. I need this part. Okay, we have seen what what primes Euler polynomial gives us, so we can now just get rid of it. And that last polynomial that we see here in this book of this type is k of n, and that is 36 n square minus 810 n plus 2753. It gives us 45 prime values. Okay, for these values starting from 0 and ending at 44. 44 because from 1 to 44 there are 44 numbers. You include 0, you get 45 numbers. All of them are prime. Okay, and then there is one a little claim, and that claim has been proved. Okay, and that claim is again about production of primes by polynomials in this way. And the claim is this: there is no non-constant polynomial with integer coefficients that takes on just prime values, only prime values. Okay, which is what we were trying to find in the beginning. That is a kind of value. We did not require only polynomial functions to be always prime producing, but we wanted some kind of function. But polynomials cannot be such a function. It cannot be that a non-constant polynomial whose coefficients are integers produces only prime values. That is not possible. So let me just write the statement here. There is no non-constant polynomial with integer coefficients that takes on only prime number values. Do you see why constant polynomials have been kept out of this statement? Why is it that this statement is false? If we include constant polynomials, it's easy. You consider this constant polynomial fn equal to say 3. Okay. Now, no matter what n you take, you are always going to get 3. So, that is always prime. But it is always prime in a trivial way. When you take non-constant polynomial, then the value will change. Every time you evaluate it at some integer, you are going to get some new value. So, there it becomes interesting. That's why constant polynomials have not been considered in this statement. Okay, now how to prove this statement? Contrary to what is being claimed here, suppose such a polynomial exists. Say, this polynomial always gives us only prime number values for every integer n. And also, it's a polynomial with integer coefficients. All these ai's are integers. Then what would go wrong? Where ak is a non-zero integer, so that the polynomial has degree k. K is a non-negative, we are assuming that this is non-constant, so k cannot be 0. K has to be positive. All right. Now, you choose any integer n whatsoever. Okay, say n equal to n naught, anything. Okay, if you wish, you can take n equal to 1 also. Here, however, the author has chosen n. Now, no matter what n you take, f of n is going to be prime. That is our supposition. That means this is prime. Say we denote it by p, f prime. All right. Now, for any integer t whatsoever, positive, negative, 0, anything, for any arbitrary integer t, we have this. So, let us now calculate n naught plus pt and see what we get. We use the expression for f of n and replace n with n naught plus pt. So, we are going to get this n naught plus pt to the power k plus ak minus 1 times n naught plus pt to the power k minus 1 plus a2 times n naught plus pt whole squared plus a1 times n naught plus pt plus n naught. Alright. Now all these powers can be expanded using the binomial theorem, and there is in fact no need to write everything, the whole expansion, but we just need to note that in all such expansions there will be these terms n naught to the power k, n naught to the power k minus 1, n naught squared, n naught to the power 1. Okay. Now if we collect all those terms together, we are going to get ak n naught to the power k plus, from here we are going to get a k minus 1 n naught to the power k minus 1, and so on. Let me continue on that side. Okay, so if one continues like this, from this term for example, one will get a2 n naught squared, then from here one gets a1 n naught, and let us also include a naught in this part of the sum, plus there will be many things more, but in all those things you are definitely going to get p, okay, as a factor. I mean, one term in say you concentrate on the binomial expansion of this, the first term, if you start the expansion like that, is going to be n naught to the power k. The second term will be k times n naught to the power k minus 1 times pt. In the third term you will get p squared t squared. So the exponent of pt term keeps on increasing and the exponent of n naught keeps on decreasing. So except this term n naught to the power k, in all the other terms we will have p, and this is going to be the case for the other expansions also. So you end up having many more terms. In all of them you have at least p. In some of them you will have p squared, p cube, and so on, higher powers of p, but in all of them you will get p. So we can take that p common out, and we will be left with a polynomial of t, okay, q of t, which after all is just an integer. If you just think about it, everything is an integer right here. So that is why you get an expression like this. Now if you then look carefully, this is nothing but f of n naught plus p times q of t, but f of n naught is p. So you can take p outside and have this. Alright. So this of course is an integer after all. We have a polynomial with integer coefficients. We are evaluating it at some integer. We are going to get integer as its value, that is equal to p times another integer, which means that p divides this. So p divides this. However, let us again recall our supposition that f is always going to give us prime value. So that means this is a prime number, and that is divisible by another prime number. This is only possible when this prime is actually equal to this prime. Otherwise, it's not possible. A prime number cannot divide another prime number. Okay. Since this is prime, we must have f of n naught plus pt is equal to t. All right. Okay. Now, what can we conclude from this last equation? Keep in mind that t was any arbitrary integer. So, whatever conclusion we have here, I mean this equation, this is true for all integers t. However, if you now consider this polynomial, f of n minus p, this is also a polynomial, right? And it's actually this polynomial. I won't write that many terms, but a1n plus a0 minus p. This is also an integer polynomial, a polynomial with integer coefficients. And what does this equation tell us? This equation tells us that n0 plus pt is a root, or it's also sometimes called a zero, of the polynomial f of n minus p for all integers t. However, is this possible? No, it is not possible. Why? Because we know that this, just like the original polynomial fn, is also a non-constant polynomial. Its degree is k. Remember that we remarked there at one point that k has to be positive because it is non-constant. And we know that such a polynomial can have at most k roots. Here, however, we seem to be having infinitely many roots of this form n0 plus pt due to the fact that t can take all the integer values. This is sheer nonsense. It goes against that property of polynomials. Having at most that many distinct roots, equal to the degree of the polynomial. So that's a contradiction. And this contradiction proves that our supposition is wrong. So no such polynomial can take only prime values. It has to take composite values. So the hope of finding a function which gives us only prime values is dashed. I mean, dashed means for integer coefficient polynomials, you cannot find such a function. However, something was done by W.H. Mills in 1947. These dates have become so in the past right now. What he proved is that there exists a real number a positive real number such that this function r to the power 3 to the power n, and where the square brackets indicate the greatest integer function with which we are familiar. always, or let me write like this, is prime. Sorry, why did I write r here? It's a function of n. Sorry about that. Is prime for all positive integers n. So this is a prime producing function. It's always going to give us prime. No matter what value of n you put, the result is a prime number. So isn't it nice? It is nice, but there is something which prevents it from being so nice. I mean, at first glance you may think, okay, we have found such a function. We have found, but it's a theoretical find, in the sense that Mills proved that there exists such a positive real number r for which this will be a prime producing function. However, what r actually is, no one knows that. Okay, so it's a purely existence result. Moreover, Mills function does not produce all the primes. That is also known. It keeps on giving us primes. That has been theoretically proved. But because we do not know anything else about R, only that it exists, so it fails to be a practical prime producing function. And this is where this section ends, and today's video also ends. After this, of course, we have the exercises which we will solve in the community section. So that's just it for tonight, folks. See you in the next upload. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.